Hey class. Let's see, we're going to continue our little journey here and look at unique factorization domains today. Let's just sort of keep track of what we have. We have integral domains. We have, I'm not writing these in any particular order, which is probably bad, Euclidean domains. Maybe I'll fix this in just a minute. Let me abbreviate this ED so I can change that in a minute. We have principal ideal domains. What else? I feel like there was one more. But anyway, this is oh, we had what I call GCD domains. I think actually that's something we're going to talk about today. And finally, we're going to have UFDs. Okay, so we get all sorts of domains here. Oh, and then we had Ethereum, all sorts of things. Okay. Maybe a good exercise would be to just put these in order. Exam question. That would be nice. Okay, anyway, today is UFDs, right? So this is our thing today. And part of the idea with UFDs is, when we're dealing in Z, and a lot of what we're doing here, if you notice, is kind of trying to generalize from Z up to other things, in particular, f of x, where f is a field, right? Polynomials with coefficients and fields. Here we have these two notions that are the same. We have P divides A implies A equals 1 or A equals P, right? So that's one of our common definitions of prime, and the other one is if P divides AB, then P divides A or P divides B. Okay, and here we want to sort of pull these two notions apart because they're not actually the same. So officially we're going to have definition. Oh, and one thing I should say, and I say this in the notes, here we're always working in integral domains, so I don't have to worry about commutativity or unit or zero divisors, right? And so the definition is that P in R in an integral domain is prime. So we have this definition already. Remember, because we have the notion of prime ideal. So all this definition is going to say is that the ideal generated by P is a prime ideal. But I'll just say it again here. So if and only if P divides AB implies P divides A or P divides B. Okay, so this is equivalent to saying the ideal generated by P is prime. Let's see, is that really true? I'm not sure about this, like in a PID anyway. I haven't really thought that through, so that may not quite be true. This was certainly a condition to show that, that an ideal is prime if and only if for every A times B, which is in the ideal, either one of A or B is in the ideal, right? Yeah, no, this is right. Yeah, this is right. Yep. So yeah, we don't need that. Anyway, that's our definition of prime. So right, this thing, right? And the other definition is P is irreducible. IFF. Okay, now we're going to say, how if P equals AB, then P equals, well, let's see, how do I want to say this? 1 of AB. Okay. Well, there's I guess there's two equivalent things I could say. Either A or B is a unit. Now, before we just said was 1, right? But in Z, the only units are plus or minus 1. So I should have said plus or minus 1. Or the other option is that P is an associate of A or P is an associate of B. Remember, that just means that this is just equal to a unit times A. So these two things are saying the same thing. So those are kind of the two definitions we have here. And let's see. So one thing is this. I'm just going to sort of try to follow my notes here a little bit carefully. Yeah. So one thing is this, that P prime implies P is irreducible. Okay. So why is that? So suppose P equals Rs. So we're assuming P is prime, right? I want to show P is irreducible. So suppose P equals R times S. I need to show that either R or S is a unit, or I need to show that P is, an associate of R, or P is an associate of S. One of those two things. In particular, we have here that P divides R or P divides S. Let's see. And what I do here is I say suppose that P divides R. Then what does that tell me? Well, it tells me that R is equal to, P something, Q. I'll just call it Q, right? Because that's what it means for P to divide R, right? Remember, we're just in some integral domain here, right? Okay, so I have here now that P equals Q PS, right? And so, I mean, first of all, this looks suspicious, right? Because, what P divides, how do I want to say it looks suspicious? So R is this, so P, I guess P divides R, and then R divides, let's see, how do I want to say this? P divides R. Yeah, and R divides P, right? So that looks suspicious, right? We have P divides R and R divides P. I mean, that, maybe that already gives you some thought that something strange is going on. And maybe we could just show that this implies that these are associates. Maybe that's exactly what I'm doing here. But so anyway, here I can rearrange this into this, and this is equal to P times 1 minus QS. Yeah, okay, well, this is another good exam question. Just think of them up as you go. That's how exams get made. And what we know is that this is equal to 0. Right, now here we use the fact that we're in a, integral domain, right? So that can't be 0. I mean, sorry, this is equal to 0. This P is not 0, right? That's a thing that's our prime right now. And so this must equal 0, right? But that says that QS equals 1, and that says that S in particular is a unit. And that's what we wanted to show, right? We wanted to show that one of those two things was a unit, okay? So this is nice, right? So in general, the notion of prime implies irreducible. Now, wouldn't it be nice if it went the other way? I mean, maybe it'd be nice. Maybe it wouldn't be nice, because then things wouldn't be so interesting, okay? But it doesn't go the other way. And so let's just sort of go through this argument, because it's nice to have this example. So in, sorry, in z square root of minus 5, this will be our example. You can come up with other ones. This is just the one I have here. What I have here is this. I have that 2 minus square root of minus 5 times 2 plus square root of minus 5. So this is just multiplication of conjugates, right? So I get this squared plus that squared. So this is 4 plus 5, and that's equal to 9, right? Okay, so here we have that 3 divides 2 minus square root of minus 5 times 2 plus square root of minus 5, because 3 divides 9, right? But 3 does not divide 2 minus square root of minus 5, right? Now, let's see, do I have an argument for that? 3 that are irreducible. Yeah, well, let's see what I actually say here. I say it here. Maybe we'll come back and see if I can give an argument for that. Let's see, I do want to see that 3 and these other things are irreducible, right? And so for that, right, so let's take, I'm just going to do one of these. Let's take this one. Let's take 2 minus square root of minus 5. Okay, so certainly the argument for this one and the one for 2 plus square root of minus 5 should be the same. So this is going to be just the thing that I'm calling here z, for example, right? We're going to use this arithmetic norm, right, which is just like what we do with complex numbers, right? So it's really just z bar again. Okay, but z bar here is just where this is the square root of something, right, that we're interested in. So we're going to change plus to minus and minus to plus, right? So in this case, this would be 2 minus square root of minus 5, whoops, times 2 plus square root of minus 5. That's z bar, right? And we just saw a minute ago that's 9, right? So that's clear. It's also true, right? Same kind of argument that n of 3 is 9, right? So both of these, are 9, right? So that's 9. N of z is that thing there, right? Is 9. Okay. So now suppose z equals a product, right? So let's say, and I'll just try to use the same notation here. So AB, right? So one of the properties of this norm here is that n of AB equals NA in B, right? And the proof for that is really straightforward. So n of AB is AB bar, right? And this is A bar. Prove this exactly how you would for complex. There's nothing sophisticated going on here, right? And this just by definition is NA in B, right? So we have that sort of property. So now notice, by the way, that what we're getting out here is just an integer, in fact, a positive integer, right? And so here we have that NZ, which is 9, right, is NA in B. Okay, but 9, of course, is 3 squared, right? So we have, basically two possibilities. We could have that NA equals NB equals 3, right? So that's one possibility. Okay, and then let me see. So what was the problem with that? I think I just want to say that, hold on a second, I'm going to pause this. Yep, sorry, little brain fart there for a second. Remember, these are squares, right? Another way of writing what we have here is that, oh, whoops, no, that's not quite true. Okay, sorry, I'm back. Yeah, this is actually clear, but there's something kind of fun here. So, so let's show that this is impossible. Whoops, did not mean to do that. Yeah, it's good for you to see that even I have to think, right? Okay, so let's show that this is impossible. And this is actually kind of an interesting fact. I won't dwell on it too much. This is in the notes on Gaussian integers, more specifically. Here I'll be real simple about it. So suppose this happened, right? So suppose A was, and I got to come up with some more letters. Let's say alpha plus beta I, right? Oh, not alpha plus beta I, alpha plus beta square root of minus 5. Right, that's the situation we're in, right? Where in this case alpha and beta are in Z, right? Then in A, right, is going to be alpha squared plus beta squared times 5, right? Remember, this is like the length of this, right? The I, you get this I times I thing, right? And that's how this works. All right, because well, okay, let me know. You can check that. That's the way this works, right? That's the way the norm works. And so the question is, can this possibly be 3, right? And well, there's not much room. I mean, this thing clearly has to be 0, otherwise it's bigger than 5, right? And so this thing is 0, and alpha squared can't be 3. Remember, these are just integers, right? So alpha squared can't be 3. So of course that's impossible, right? So that can't happen. So what we actually get here is that NA equals 1 or NB equals 1. And now what we need to show is that if NA equals 1, then A is a unit. But this is trivial too, because what is NA? Well, it's A bar, and that's equal to 1, right? And so that tells me precisely, right, that A bar is A inverse. right? So yep, it's a unit, right? So here what we've gotten is we've gotten, suppose we could split z, which was this thing here, into AB, right? Then it turns out that one of those two things has to be a unit. And actually, we never used anything special about this, right? We just used the fact that its value here was 9, right? So the same argument works for 3. 3 also works, right? So what we have here is we have 3 and 2 minus root 5 and 2, sorry, minus 5 and 2 plus root minus 5 are all irreducible, right? So those are all irreducible. Notice that what this means is it means 3 equals 3 times 1 equals 2 minus square root of minus 5. This will come up in a minute. 2 plus square root of minus 5 are two distinct ways of writing 3 as a product of irreducibles, right? I mean, one just being itself and the other one being like this, right? So there's not a unique way of doing that, right? So that's going to be important in just a second. And I think that was everything. I guess the one thing I didn't show here is this. I was needing to show that 3 doesn't divide 2 minus square root of minus 5, right? Let's see if we can do this sort of like I just did a minute ago. So let's say if 3 does divide that, then what I have is I have 2 minus square root of minus 5 is equal to 3 times something in our some a plus some alpha plus beta square root of minus 5, right? I'm just going to call it a w for now, right? And then let's try this again. So I get the norm of this. I think we just use the norm for everything here. It'd be the norm of 3. Yeah. See, you can see what's happening right now. And then norm of w, right? But the norm of this is 9, right? The norm of this is 9, right? So the norm of this must be 1, right? That's going to tell us immediately that this has to be a unit, right? And so let's see, why is that a problem? Let's see, why is that a problem? Okay, back again. So this is a problem because we have this where that's a unit, right? So we get 2 minus square root of minus 5 times z inverse, which, by the way, we just showed above was just z bar, right, is equal to 3. And that can't happen because 3 was irreducible, right? We just showed that above, so that can't happen. Okay. Yep. So okay. So this is completely done, right? So z squared. So just to keep this in mind, z square root of minus 5 is a nice example space, and you could use other things than square root of minus 5 here. So this is a non-UFD because we had not unique factorizations. I haven't even said what that is yet, but when we get there, you'll see that. And we have irreducible does not equal prime here. All right, so we get those two things. So that's a nice thing. Okay, good. All right, so now let's get to the unique factorization. R is a unique factorization domain. R is a UFD if and only if every element, so this is like prime decomposition, but we actually need irreducible for this, not prime, right? So every R and R can be written uniquely up to something up to order and associates, right, as a product of irreducibles. This is actually true in Z too, right? I mean, I can write 4 is equal to 2 times 2 and also minus 2 times minus 2, right? I mean, we consider those to be basically the same. So we do have 2 units, right? We have 1 and we have minus 1, right? And even in Z, right? So just to sort of play this out some. So this means that if I have this written as R1 times dot 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 plus times RK equals S1 dot 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 times SL, right? Where these Ri and SL are irreducible. All right, then I know that K equals L, and I know there's some sigma in SK, so a permutation of the numbers 1 through K here, such that Ri equals S sigma I, right? So in other words, I can permute these. And, oh, sorry, not equals, right? This is important too. Let's see, go erase. I keep hitting the wrong thing. Okay, erase. I want it, these are associates, right? So I can rearrange so first of all, these two sequences have the same length, and we can rearrange them so that every thing here is an associate of the thing kind of across from it, right? So like that. So that's what it means to have unique factorization. So it's unique up to order and being associates, right? So you have to be a little bit careful about that. Okay, so here's a nice little thing. Actually, maybe this is slightly out of order here. So the theorem is that if we have a GCD of A and B, right, then I'm going to say that then all irreducible elements are prime. So in particular, if I'm in a GCD domain, so in a GCD domain, all irreducible are prime. Okay, and then I'm going to show that a UFD is a GCD domain. I guess that's the thing that we're going to do. And so then we'll have the irreducible and prime are the same in a UFD. So what is a GCD domain? So this is important to get right. So here I'm going to have, if A, B is an R, right? I want to say there's a GCD of A and B. So it's going to say there exists some D. Now we're not actually saying it's unique, right? It might be unique up to units again. This is some D such that D divides A and D divides B. So it's a divisor, right? We don't have an order in R, so we have to say what we mean by, greatest common divisor, right? Maybe we should even call it like a maximal common divisor. So D divides A and D divides B, and for all D prime, such that D prime divides A and D prime divides B, it's the case that, D prime. So this should be a smaller divisor, D prime. It should be the case that D prime divides D, right? So in some sense, D is kind of packed in with all the possible divisors, right? So that's the idea. Okay, let's also just do this real quick. If we're a UFD, then we're definitely a GCD domain. Okay, so I'm not proving the theorem yet. I'm just sort of getting some consequences from it first. Well, why is that? Well, this is like the grade school version of finding a GCD. Once we're a UFD, we have like A equals A1 times times AK, and B equals B1 times BL. Right now, these are two different things, so the lengths and stuff don't have to be the same. And what we do is we collect up common terms. So let GCD or let D. Let D equal the common terms with multiplicity. I mean, some of these might be the same, right? I'm not saying that these are powers of a single prime. These may be they may be like 2, 2, 2, 2, 2 several times, right? D is equal to the product of the common elements. All right. And then, so that's like putting together all the possible irreducibles that we have there that are in common with these things. And what do I mean by common again? I mean up to unit, right? I mean, we're always saying this up to unit, right? Because we don't care about multiplying by something where we have an inverse. Again, in Z, that's like multiplying by plus or minus 1. That's irrelevant for division, right? And then the claim is that this D, so this D is GCD of A and B, right? Clearly, D divides A and D divides B because we just multiplied together factors, right? So that's clear. And if D prime divides A and D prime divides B. What do we know about that? So we know that D prime divides this product of things, A1 through A. Well, let's see. So here I guess here we have to do a little bit of an argument. So D prime is itself D1 through some DS, for example. Do I have S? Nope, S is fine. DS, right? And oh, sorry about that. And then I have here that D1 through DS divides, for example, A1 through AK, right? And so what happens, since these are reducible and those are reducible, right? D1 has to be, one of these things, right? So basically you just keep canceling things off till you have the stuff that's left over, right? And you do the same thing. I'm doing this a little bit sort of in the air, a little bit hand wavy, because I think the idea is enough here. I don't know, maybe to do it formally, you'd have to do induction or anytime you have dot, dot, dots, usually there's an induction around, right? But basically I can cancel, all the things here and all the things there. So I'm left with some, subset of this and some subset of that. If there were anything in common, I would have put it in there, right? So every one of these things, so what am I showing? So every one of these DI definitely divide D, right? Because these are things that are in common to both of these sets, right? And D was the product of all the common elements, right? But then the whole product of these things, so then D prime divides D. Okay, that's an argument, right? Okay. Again, your proofs, right? When you write down a proof, it should not look like this. It should look nice. This is sort of like train of thought thinking through an argument here, but that works. Okay. Yeah, I guess that's in. Yeah. Anyway, that's what we have there. Okay, so now I want to show. Suppose we have GCDs. Oh, and by the way, once we have GCDs, so if A and B, if we have a GCD, A and B, then we also, of course, have the LCM of A and B, and you can check that these are the usual, what you would expect them to be, and that's going to be just A times B over the GCD, right? And you have the property that A times B equals the GCD of AB and the LCM of AB, right? As you'd expect, right? And you get that, let's see, what do I want to say? Yeah, I guess you get that you get for free here that the least common multiple of A and B is equal to A times B up to units, right? If and only if the GCD is a unit, right? So being relatively prime here wouldn't be the GCD is 1, it'd be GCD is a unit, right? That's kind of the corresponding thing here. So we're going to use this notation, and by the way, being an LCM domain would be sort of corresponding to being a GCD domain, and those are equivalent. Okay. Let's see, and the timer for this one's about to run out, so I'm going to stop this one and start a new one. Okay, this is the third take of this. For some reason, my recording thing is not working. Okay, we're trying to prove that that for in a GCD domain, so GCD of A and B exists for all A and B, then irreducible elements are prime. Remember, before we showed that prime are irreducible. Okay. It's a cute proof, and I guess I stole it from Wikipedia somewhere, right? I mean here, right? And then there's also, if you look here, there's the notions of primal ideals. I mean, you could just keep going with this, right? But the idea is this. So we have, we just have R and R, and we have that whenever R divides AB, so this is looking like prime, right? And that's going to imply that R is equal to ST. Well, that's looking like irreducible. And right, S divides A and T divides B, right? So we want that sort of thing. So it's kind of a combination of these two things. This is R and R is primal if this happens, right? So it's pretty clear that R is prime if and only if R is irreducible and R is primal. So one direction is we've already done. So if R is prime, then it's irreducible. We've proved that already. And in the case that R is prime, of course, we get better than this. We don't even need this. We just get that that R splits into a unit. And anyway, we get that, right? So that's clear. So it's the other direction, right, that we need to show. And that's also pretty clear, but it does take a little bit of an argument. So let's see why this is true. Oh, no, sorry, this doesn't require much of an argument. This is actually clear also, right? So if R is irreducible and primal, right, so let's suppose P divides AB, and P is irreducible and primal, right? So suppose that, right? Well, then, so what it says is that P equals some other ST, where S divides A, or and T divides B, right? But we're assuming that P is irreducible, so one of those, so like S is a unit, or T is a unit, one of these is a unit, so we may as well assume S is a unit. Right, but then if S is a unit, then P and T are associates, right? Because we have a unit times something. And so T dividing B is just equivalent to P dividing B, right? So we're in that kind of situation. So P divides AB, and it's irreducible and primal, and we split up P like this, right? So, I mean, being irreducible says, one side or the other is a unit, and the other one is basically P, is an associate of P, right? Then we get that P divides B, right? And the other option would be that S is not a unit, but T is, and then we'd have P divides A. So one of those two cases holds, right? So this is actually clear. So we're prime if and only if those two things. And now the trick to this proof is showing that in a GCD domain, every element is primal. That's what we need to show. Okay, so this is the main part of the proof. Okay, so how does this go? So we take A and B in R. Okay, so now I'm going to just sort of cheat. Whoops, whoa. Let's come back to the right part of the proof here. Sorry, and we have R, we have R, another element of R, and R divides AB. Okay, and so what do I get here? Well, I do have D equals GCD of R and A. By the way, I mean, to go with this argument, just sort of play with it. We need to use that we have a GCD. I'm going to just sort of show you that things work, and you can think about if there's maybe a prettier way of doing this. So I'm going to let M be the LCM of R and A. And remember what we have here is we have that that R times A, right, is equal to D times M, right? We had that above, right? Because we have the GCD times the LCM is equal to the product of the things we're doing that in, right? So that's good. So all we need is we need these things to exist in order to write that down, right? Okay, so we have that, and so then I have that dB, right, is actually R times A over M. Now, why is that times B, right? So the B is there. I'm just getting D. D is equal to R times A divided by M, and we know this is an integer because we have this relation there, right? Okay, and so then I let and so then we have that R divides dB, right? We know that R divides dB because it divides this side, so it has to divide that side. And so I let S equal to R over D, okay? And we knew we could do that anyway because we have, that's the D is the greatest common divisor there, right? And S divides B, so S divides B, right? Why is that? Because what am I doing here? So S is R over D. So oh yeah, right here, right? Because of this, right? So S divides B, and we have here that R equals, I'm going to say SD. Let's just verify that. So this is R over D. Well, that's trivial, right? Times D, right? So it's like that. And so we have all together here, right? So R is equal to ds, and D divides A, because again, it was the GCD, and S divides B, right? So it was just kind of a construction using the GCD and the LCM, right? That's what we needed to show, right? We started off with R equals AB, we got R equals DS, where D divides A and S divides B. And so R is primal, and R wasn't chosen to be anything special, it was just any old element in there, right? These are any old elements in there, so every element is primal, right? And therefore, in a GCD domain, we have that every irreducibles and primes are the same, right? So the next thing we're going to do is argue that a PID is a GCD domain, and then argue some slightly more general things. But I'll make that into the next video.